Let's talk about the configuration of ionic substances. We've already talked about the electron configuration of the neutral atoms, but as you well know, plenty of compounds and plenty of elements can develop charge. And so we need to be able to determine the electron configuration in the case where charge is actually present. And for the examples here, I'm going to look at the nitrite ion, the chlorine 3 plus ion, the nickel 2 plus ion, arsenic 3 plus, and rhodium 1 plus. What you basically have to do is start by drawing out the configuration for the neutral atom. So you draw out, or you come up with a configuration for neutral nitrogen, the configuration for neutral chlorine, neutral nickel, neutral arsenic, neutral rhodium, which is basically what we did in the previous video. We came up with the following configurations. And now what you do is for every plus charge that you have, you remove electrons. For every minus charge that you have, you add electrons. But a better way to look at it is you simply look at the charge and you subtract it from the number you have here on the on the final orbital level. So in the case of 3 minus, you say, okay, well, this is 3 minus minus 3, which is the same thing as 6. Or in the case of 3 plus, you say, well, that's 5 minus 3, which is 2. In the case of nickel, you say 8 minus 2, which is 6. In the case of arsenic, you say 3 minus 3, which is 0. In the case of rhodium, you say 7 minus 1, which is 6. And basically that gets you into the correct configuration for each one of the elements. Okay? But I'm going to now introduce something else, which kind of adds a layer of complexity. And this has to do with transition metals specifically. I subtracted already or added the corresponding electrons for nitrogen, for chlorine, and for arsenic. But when it comes down to nickel and rhodium, you can still subtract the 2 from the 8 to get 6, and you can still subtract the 1 from the 7 to get 6. But what you also have to do is, once you have taken care of that, all of the electrons of the preceding s orbital are added to the d orbital itself. This happens if and only if the transition metal has a charge. You don't actually do this when the transition metal is neutral, but once you have this charge, the s electrons become higher in energy than the 3d orbitals, and so they actually end up being delivered to the d orbitals altogether. So instead of this being 4s2 3d6, you'll end up with simply, yes, you subtract the 6, but then the s become added to the end point, right? We do the same thing here. So all the s get delivered to the d. So instead of this being 3d6, it's now 3d8, but you no longer have s electrons. And over here, instead of this being 4d7, or 4d6, excuse me, the 2 electrons of the s get dumped into the d. So you no longer have s electrons, all you have is d electrons. And once again, this only happens if and only if the transition metal has a charge. That's very important to remember, because this will not be something you do if the transition metal is neutral. There's going to be some exceptions that I'm going to show you on the next section that do involve transition metals, but you don't exactly do this, at least not to this extent. So charge on the transition metal, remember to take all the s electrons into the d. With the one caveat being that you cannot have more than 10 electrons on the d, right? Alright, now as far as drawing all of these things, you could still do the same thing we did before, which is start with the electron configuration of the neutral element or the drawing of the neutral element and simply subtract the charge in terms of electrons, right? So if you subtract minus 3 from the 3 electrons you have, you're going to end up with 6. Over here you only have 2, so you draw 2 electrons. For nickel you have 8 d orbitals, so you draw the you have 8 electrons in the d orbital, so you draw the 8 electrons there. Notice that I'm not even bothering putting the box for the 4s because the 4s doesn't have any electrons. And in the case of rhodium, the same is true. I don't even bother drawing the 5s box because it doesn't have any electrons. But you still want to make sure that you have the proper number of electrons for the rest of the stuff. For arsenic, since the 4p orbital is completely free of electrons, I don't even write it down or draw it out in the box. Alright, now the last part that I need to mention to you are the exceptions. And this is actually kind of a limited list of neutral elements that have an exception to the configuration, as you would derive by doing the method that I showed you. And this has to do with ultimately how many electrons they have present. But the elements that have an exception, the neutral elements, are the following transition metals: copper, silver, and gold, which are basically group 11 elements, and chromium and molybdenum, which are the group 6 elements. If you actually look further into this, just out of curiosity, you're going to find out there's about 20, maybe 21 elements that actually have exception rules to the configurations. But in Chem 11 or Chem 201, we only bother with this 5 in particular. All right, so I'm going to analyze what happens for those 5 elements. All right, so chromium, if we draw the electron configuration, and we're going to stick to the noble gas shorthand notation, notice that the noble gas that precedes chromium is argon. So I would start with argon, and then I would say 4s2, and chromium is on 1, 2, 3, 4, so that would be 3d4. For molybdenum, the preceding noble gas is krypton, so we'll say krypton, 5s2, and then 4d4. For copper, I would say argon followed by 4s2 and 3d9. 9, since this is in group 11, 11 minus 2 is 9. Same thing for silver. This will be d9, this will be d9, and you will have your s2 preceding it, right? So the configurations will be the following: 4s2, 3d4, 5s2, 3d4, 4s2, 3d9, 5s2, 4d9, 6s2, 5d9. That's the sequence for each one of those neutral elements. All right, now if you draw out what this looks like here, you can actually start seeing a little bit more of the issue that we're having. If you draw out the configurations that we get directly by looking at the periodic table, what you're going to notice is that for chromium and molybdenum, you actually have one less electron than it would be necessary to have a complete half shell completed. And for copper, silver, and gold, you are one electron shy of having a complete shell in the d orbital set. And so what happens is that for this particular element, one electron from the s is actually delivered to the almost half full and the almost full shells. So instead of having a 4s2 set, you actually end up with a 4s1 set. And instead of having the 3d4 or 3d9 sets, you end up with the d5 and the d10 set. Now the reason this happens is because of something known as the exchange energy. And to put it simply, the exchange energy just kind of tells you or arises from the fact that all of these electrons are basically the same particle. So it doesn't really matter which one of them you have on the left box or the right box or the middle box. The fact that they're all the same type of particles means that you could arrange them every which way and you still have the same configuration. But the more spin up electrons you have present in here, the more probabilities you can end up with in terms of how you can arrange them. And this is kind of a question of combinatorial mathematics. If you've ever taken statistics, you've probably gone through the equation of combinations and permutations. This will be one of those problems where you actually find how many combinations there are that can allow you to come up with this overall arrangement. And since you have 5 spin-up electrons, you end up with a lot more combinations that allows you to get this configuration than if you only had 4. And the same thing here. You have 5 spin-ups and you have 5 spin-downs. So you have basically maximized the way in which you can arrange these electrons. It's basically double the amount of exchange energy that you get for the D5s. But that exchange energy and that overall way of shuffling the electrons and still get the same result, it's kind of one of the essence of a thermodynamic property known as entropy, which we have not discussed in this class, but you will actually talk about in your upcoming, in the next series of your chemistry courses. But it is there, and it kind of accounts for the fact that, yes, you have this anomaly in the configuration. And you are required to remember that chromium, neutral chromium, neutral molybdenum, neutral copper, neutral silver, and neutral gold. All of them have the anomalous configuration compared to the rest of the neutral elements. Alright, so with that we've actually finished the entire lecture. And yes, it's quite a bit of material, but hopefully this lecture series has helped you kind of maneuver through the entire sequence of not only steps but concepts associated with quantum chemistry. In the next lecture series, we're actually going to dig deeper into the idea of looking at multi-electron atoms and use some approximations to calculate values that otherwise you would think you just have to be given from a table. This time we're actually going to calculate them from scratch. Alright, so see you in the next lecture.